All right, here we go. In this one, we're going to look at the physics journal about Hooke's law. And the question that's guiding our notes today is how do springs apply forces? The big idea here is that the force applied to a spring is proportional to the amount the spring is stretched. Let's just remember that that word proportional means that um, right? Like if you double how much you stretch the spring, that's going to mean that you're going to double the force. Or if you triple the amount the spring is stretched, that's going to triple the force. Or you know one half how much the spring is stretched, that's going to one half the force. It just means by whatever factor you change, either the stretch, the force is going to change by the amount. If we look here, based on the right from the lab, we've changed what our number was, what our slope was. We've changed, put a k in there instead, and that's called the spring constant. And that basically just describes the stiffness of the spring. More on that in a second. Delta x would be the distance that the spring is stretched. And again, the reason that it has a delta is usually you're subtracting like the length of the spring minus the original length of the spring, right? So when you've stretched that spring out, it is now longer, and then you have to subtract out the initial length of the spring, hence the delta there, right? Because remember, delta is just final minus initial. So that'd be the final length of the spring minus the initial length of the spring. Then it says here that the spring constant is a number that represents the stiffness of the spring. So basically, if you have like a spring that's just really hard to stretch, like you really have to put a lot of effort into trying to stretch it just a little bit, which we describe that as maybe like a stiff spring or kind of a rigid spring, then that would have this high spring constant, like a high big K. And if you had, like thinking about the rubber bands, it's like a more like a broccoli rubber band versus one that's really easy to pull, would have right a smaller K value, like one of those tiny little thin rubber bands. It has units of newtons per meter, so mathematically it's the amount of force to stretch the spring 1 meter. So that right, if you had a spring constant that was like right, if K was like 100, that means it's 100 newtons to stretch that spring 1 meter. And if you had so that's going to take a lot of force to stretch it 1 meter versus if it was like 5 newtons per meter, obviously, right, it's a lot less force to stretch it 1 meter. All right. So let's go ahead and take a look at our example problem number one here. It says that we have a force of 4 newtons is applied to a spring, stretching it 10 centimeters. What is the spring constant? So right, we can actually just use the Hooke's law for that. F is equal to kx. We're looking for, well, k delta x, right? But they've given us delta x because they told you how much it's stretched. So um, we know that the force is 4 newtons. We're looking for K, and it's stretched 10 centimeters. We got to make sure we change the centimeters into meters. So that's 0.1 meters. You just move the decimal point two places. Basically, you divide by 100 because there's 100 centimeters in a meter. And that's going to give you 0.1 is what we have to put in there so that it's in newtons per meter as opposed to newtons per centimeter. And then you divide, right? That's going to give you 4 divided by 0.1 is equal to k. And that's going to give you that k is equal to, well, that's going to be 40, I believe. Just let me double check that. Oh, so that's going to be 40 newtons per meter. All right, great. Let's move on to example 2. And there we are. Okay, so now we have 2 different springs are used to produce the graphs below. So this is basically like the Hooke's law lab that you just completed, except that, right, like we just plotted 2 springs on the same graph. So, like here's one spring produces this graph, and then another spring produces that graph. 2 different springs are plotted on the same graph. Um, so obviously we have different slopes, right? Spring 1 has a steeper slope, spring 2 has a flatter slope. And let's remember that the slope of this graph is the spring constant, right? That was how we calc what we got in the lab. And also remember that this k was the slope of the graphs. That's how we got that. Um, so anyway, it says which spring would be harder to stretch. So if we look at this, right, this one has a steeper slope. That tells us the K is bigger. And so that tells us that basically that one's going to be a stiffer spring. We can look at it, right, in order to, if we look at the two springs and we just compare them, maybe we take this point right here, right, to stretch the spring 0.2 meters, so that would be 20 centimeters. The spring 2 only would take 5 newtons to do that, but spring 1 would take 20 newtons to do that. So you're just going to have to apply like weight, right, like almost 5 times as much force to get spring 1 to stretch 20 centimeters. So, um, right, so we can say spring 1 would be harder to stretch because steeper slope, telling us the spring constant is greater, something like that. So the next one is, what is the spring constant K for each spring? So basically, again, those are the slope of those lines. So we just need to calculate the slope. So that would be the rise over the run. So you can just take any 2 points that you would like and to calculate the slope. So let's see here. We could just do this one. So this goes up 10, 20. That goes up 20 and then over 0.2, so 0.2. So, so for spring 1, so I'll just call that K1. Right, again, rise over run, it goes up 20 over 0.2. So that's just going to give us 100, I believe, 100 newtons per meter. Um, spring constant 2. So we can do kind of the same thing. That's going to go up and then over. So again, that's gone up. We're at 5 right now, 5, 10, 15. That's going to go up 10, right? And then over 0.2, 0.4, 0.4. So that's going to go, rise would be 10, run would be 0.4. And so 10 divided by 0.4 is 25 newtons per meter. Oh shoot, sorry, you can't see that. There you go. All right. Last question. Spring 2 is stretched 1.2 meters. What force must be applied to do this? So basically, we can just take our F is equal to KX equation. And we know that it's spring 2, right? So that's this one over here. So we're going to put in the 25 newtons. It's stretched to 1.2 meters, or stretch 1.2 meters. Put in the 1.2 there, and right. So just 25 times by 1.2 is going to give you 30 newtons. And there you go. All right. Thank you very much for watching. I hope you found this useful. Goodbye.